In this video, we're going to work example problems where we're given a sequence and we're asked to find the limit of that sequence. And so more specifically, what we're going to do is we're going to determine if the sequence is convergent or divergent. And if it's convergent, then we want to find what the limit is. Okay, now for each of these problems, when we're given a sequence, we're actually going to be given the sequence formula for the nth term, like shown here. And it's always going to be a non-recursive formula. In the next video, we're going to work an example or two of finding the limit of a sequence when we're given a recursive formula for the sequence. But however, just note that there are sequences where you can't give a formula. There's no way that you can't find a formula for the nth term of the sequence. But even in those cases, you can still you can conceptually think about the idea of what the limit would be. All right, now, before we get started, last reminder that I keep saying limit. I'm not saying limit as, something approaches something. And the reason is because when it comes to sequences, it makes no sense to talk about the limit as like n approaches a number. Okay, we talked about why that is, and you can think about that. I'm not going to go explain it here again, but it only makes sense to think about the limit of a sequence as n goes to infinity or perhaps minus infinity. But most, or if not all, of the sequences that we deal with in this calculus course, and really just in all situations, are going to have a start point. They're going to start most of the time at like 1 or 0. The nth term with n starting at 1 or 0. And so in that case, there's only one. When you say the limit of a sequence, there's only one. That only can mean one thing as n goes to infinity. Okay, so let's get started. Let's find the whether or not this sequence is convergent or divergent. And if it's convergent, we're going to find what the limit is. And, it doesn't tell us where this starts, but it doesn't matter because we're analyzing this as n goes to infinity. Okay, so for any problem like this, to me, the first place to start is you look at the sequence formula and you say, can I replace the n with an x? And that doesn't violate any, there's no issues with that. Okay, so by replacing n with x, that means that in here, you can only input an integer. But if we replace this with an x, then that you can input any number, right? It doesn't have to be just integers. So can we do that here and there won't be an issue? So that would mean that we would have an f of x is equal to x plus x squared over 3. Yeah, there's not going to be any issue there. You might say, well, what about dividing by 0? Well, we're not even thinking about that. We're thinking about x going to infinity. So there's no issue here. Now you might be saying, well, when would there be an issue? Well, think about a factorial. Factorials, the definition of a factorial is it's only for integers. You can't put into your calculator the factorial of, you can't put into your calculator 1.5 factorial. That doesn't exist. So you can't say this doesn't, you can't do this. Okay? But even outside of factorials, I can't think of an example off the top of my head, but there could be some examples where you have an issue. All right. So since we can turn this into a regular function and there's no issue, then what we can do is just take the limit as x goes to infinity of this. And whatever this limit is, that's going to be the limit of the sequence. And this comes from this theorem here that we saw in the textbook section. If the limit as x approaches infinity of just a function is equal to L, and you can just take the x and replace it with an n, and now you have a legitimate a sub n, where n is an integer, then the limit as n approaches infinity of a sub n is equal to L. And this is a good illustration of it. So, we can assume this sequence is starting at like 1 or 0 or something like that. It doesn't matter. But the idea is you have the f of x is the solid line, and the corresponding a sub n, where you replace x with n, is the dots at the integers. So like that's the thing. If you take the n and you replace it with an x or vice versa, and there's no issue, then you kind of like got these two functions on top of one another. One with the domain, the input n, the other with the input x, and you can see how the limits are the same, right? If you have a function whose limit as n approaches infinity is L, so if we have this function, and it's not even just L, it's whatever the limit is. If this limit is equal to infinity, so that means the limit doesn't exist, well, then this limit diverges to infinity. So the limit of the function is going to be the same behavior as the limit of if you took that function and you replaced the x with an n and made an a sub n, and there was no issue. Okay, so what is this limit? Well, let's divide the numerator and denominator by x squared okay, so now this goes to 0, so this goes to 1. This goes to 0, so this goes to 5. So this limit is equal to 5. That means that this limit is equal to 5. Okay, same idea. Can we take that n and replace it with an x? Are these interchangeable? Yeah. Okay, so if we factor out an x here, okay, so it simplifies to this. Okay, so let's just find this limit as x goes to infinity, and so the degree of the numerator is greater than the degree of the denominator. So let's do polynomial long division. X cubed divided by x squared is x. X times the divisor is x cubed plus 0x squared minus 2x. Okay, so 0x plus 2x. And now the x to the first is x squared, so we're done. So x, this is equal to x plus x squared minus 2. So, okay, that's what we want to take the limit of. The limit as x goes to infinity of x plus x squared, x over x squared minus 2, or 2x. Okay, this is infinity, and then this is 0, so this goes to infinity. So this is divergent. The limit of a sub n is equal to infinity, and it's divergent. And if we come back to the first problem, I don't know why I put that this is equal to 5. The limit of a sub n is equal to 5. And, I'm not going to put as m, you can put as n approaches infinity, but just to illustrate, sometimes you might see it like this, just the limit of the sequence is equal to 5 here. And this limit is equal to infinity, but that's divergent. It's a special type of divergence where it goes to infinity. Okay, so, I would always say the first thing to try is if you can turn this into a regular function. So this is 3 to the n over 7 to the n, which is 3/7 to the n, right, based on properties of exponentials. Okay, so yeah, we can definitely with no issues say that do this, right? Because this is like an exponential. With exponentials, you don't have to have just like integers here in the exponent. Okay, so what is the limit as x approaches infinity of 3/7 to the x? Well, this is one of those cases where with exponentials that for like, a to the x. As x goes to infinity, the limit as the limit as x goes to infinity of this is equal to, so it's, if the base is between 0 and 1, not including 1 or 0, then the limit is equal to 0. If it's equal to 1, the limit is equal to 1. If it's greater than 1, it's infinity. And we talked about this when it came to sequences, like if we have a sequence that's r to the n. In fact, we don't even need to do, if we talked about, we don't even need to use this theorem here. We looked at, we went over this case for sequences of a base to the power n. So the sequence, this is a sequence of r to the n. That's what we have here, with r is equal to 3/7. That's what we have here. And we know that the limit of r to the n, what we talked about, was that if it's 0 if r is greater than -1 and less than 1, not including -1 or 1. It's equal to 1 if r is equal to 1. It's equal to infinity if r is greater than 1. And if r is less than or equal to 1, or to -1, then it's just divergent. Like, both of these are divergent, but this one doesn't diverge to like -infinity or something like that. And we talk about why this is, because like these are oscillating is what happens. R is equal to -1. Okay, so what do we have here though? We've got an r that's between -1 and 1. So therefore the limit of 3 to the n, 7 to that sequence is equal to 0. Okay, can we write this as e? Yeah, so okay, we got the square root of x, that you can't put a negative input, but we're thinking about as like this n, and we can assume that the n's, in general is going to most of the time start at 0 or 1, but we're thinking about this being greater than 0. So there's no issue here. So -1 over something, a number, either a number, this is fine, right? So what is the limit as x goes to infinity of this? Well, let's do this to make it easier to interpret. So, okay, x goes to infinity. When x goes to infinity, this goes to 0. E to the 0 goes to 1, so this goes to 1. That means the limit of a sub n is equal to 1. Okay, so can we, is this a valid function? We've got the square root here. As thinking about x going to infinity, this is just going to be some large positive number. Square root of a large positive number is fine. Large positive number squared is fine. So yeah, this is fine. So what is the limit as x approaches infinity of f of x? And since this limit, this specific type of limit here is something that I plan on going back to the limit section and making further videos on, because I think there's potential confusion with this type of limit. I don't want to get into that here. So, but this video is not about finding limits of general functions. This is a different topic. So we can just go ahead and use our calculator, because I don't want questions to come up about how to evaluate this limit. Got the limit as x goes to infinity of x squared divided by the square root of x cubed plus 4 times x is infinity. So this limit diverges and it's equal to infinity. Okay, so here we can just say replace n with x and do the same thing we've been doing, but let's go ahead and work and see if we can use another theorem as well, just to practice. So it's this theorem here. So, okay, if we have the limit of a certain sequence is equal to L, and there's a certain function f that's continuous at L, then the limit of the sequence of the function, the sequence kind of applied into the function is equal to the function evaluated at L. And so what that's saying is that we can think about if we look what's inside the square root here, we can if we found this limit here, if we treat just this as a sequence, and whatever that limit is, the square root is continuous at that limit, then the limit is the function evaluated there. So like okay, let's say this limit was just for the sake of argument, let's say the limit of this was equal to -5. Then you couldn't say that since the square root of -5 doesn't exist, then this theorem doesn't apply. If this was equal to infinity, the limit of this was equal to infinity, positive infinity, then the square root of positive infinity is, you can't evaluate that, so then the limit of a sub n would be just infinity. That's the idea. So let's look at this inside function. So can we get the limit of that inside function? Can we replace n with x and have no issue? There's no issue here. Yeah, you could divide by, you can't even divide by 0. So this is actually, for all real numbers, there's no issue. So what is the limit as x approaches infinity of this if we divide the numerator and denominator by x squared? Okay, now this goes to 0, so this goes to 4. This goes to 0, so this goes to 1. So this limit goes to 4. Okay, so the theorem is saying that we have a function, a square root function, okay, and it's continuous and there's a sequence inside of it. The limit of the sequence is 4, and we know the square root function is continuous at 4. So the limit of a sub n then is f of 4, the function evaluated at 4. What is the square root of 4? It's 2. This limit is equal to 2. Okay, here we've got a alternating sequence, right? Alternates positive to negative, positive to negative. The theorem for this sequence, to find the limit of this sequence we want to look at, is this theorem here. So we can find the limit of the absolute value of the sequence. So the absolute value of a sub n would be what? Right? You take out this -1 to the n, because it's always just positive. Okay, if this limit, the limit of this sequence equals 0, then the limit of this sequence is equal to 0. If it's not equal to 0, then this theorem doesn't help us. Okay, so can we replace n with x with no issue? Yeah, x can't be 0, but as far as when looking at this, the limit of as x goes to infinity, there's no issue. So what is the limit as x approaches infinity? Well, this is 0. Okay, that means that this limit is 0. And since the limit of the absolute value of this sequence is 0, then that means that theorem states that the limit of just this sequence is equal to 0. Okay, what do we do here? Well, when it comes to factorials, we can't do the f of x method. We can't replace n with x because factorials, they're not defined for non-integer inputs. So with factorials, we have to, in general, you're just going to have to manipulate the factorial to try and put it into a form, either simplify it or put it into a form where you can see what the limit is. Okay, so what we're going to do here is we can rewrite, so 2n plus 1 factorial. What is 2n plus 1 factorial? If you think about it, that's equal to 2n plus 1 times 2n times 2n minus 1 factorial. Agreed? Right? This is the first term, then the next lowest term, then the next, then 2n minus 1 factorial. Okay, now in the numerator, we've got, so we can simplify it. There we go. So the a sub n is equal to 4n squared plus 2n. Well, it doesn't even matter. I mean, this limit is going to be equal to 0. This limit is, we can clearly see that this limit is equal to 0. Okay. We can absolutely think about just the sign of x. Okay, what is the limit, right, for any, this is completely fine. What is the limit as x approaches infinity of sine of x? This does not exist. It's an oscillating discontinuity, right? It just oscillates between 1 and negative 1. So this limit, this limit doesn't exist either. Okay, so this we can rewrite as, okay, now can we replace n with x? That shouldn't be a problem at all. As x goes to infinity, these are both, this is completely fine. So what is the limit as x goes to infinity of x squared over e to the x? Plugging in infinity, you get infinity over infinity. So we can use L'Hopital's rule. Plugging in infinity, you once again get infinity over infinity, so you can use L'Hopital's rule again. This is equal to 0. So this limit is equal to 0. Okay, can we replace n with x? That's not a problem at all. As x goes to infinity, cosine, you could put any input into cosine. 2 to the infinity, I mean, that's fine, right? Cosine squared of, so, okay, so we can say then, what is the limit as x goes to infinity? Okay, this goes to infinity. What does cosine squared of x do as x goes to infinity? This is oscillating between minus 1 and 1. So do we have an oscillating discontinuity? Well, no, because as if the denominator is going to infinity, then it doesn't matter what if the numerator, if it's somewhere between minus 1 and 1, that doesn't mean anything if this is infinity. So this limit is 0. Therefore, the limit of a sub n is equal to 0. Okay, here we could consider using the limit laws. So we could separate this up into two separate limits using this limit law, because, well, these are the limit laws for sequences, which, as the textbook talked about, is the exact same as the limit laws for regular functions. So we could split this up into two separate limits if we wanted to. But to me, let's go ahead and, can we do this? Can we replace n with x? So x can't be 0, but as x goes to, think about going to infinity, there's no issue here. Okay, so let's go ahead and take this limit. All right. as x goes to infinity, 1 over x goes to 0. Sine of 0 is 0. This is infinity. So we've got, this is an indeterminate form, an indeterminate product. Indeterminate form of type infinity times 0. That's an indeterminate product. And so what we do here is to solve an indeterminate product, we write it as a quotient. Let's put the x in the denominator. Okay, so now we plug in infinity. The numerator and denominator both go to 0. And that is an indeterminate form of type 0 over 0, which we can apply L'Hopital's rule to. So the derivative of the numerator is cosine 1 over x times the derivative of 1 over x. Okay, and then the derivative of the denominator. And so what we're left with is of just, okay, now as x goes to infinity, 1 over x goes to 0. Cosine of 0 is 1. So the limit of a sub n is equal to 1. Okay, can we replace this with x? I mean, that's this method is the method you'll use most often for limits of sequences, just replacing the n with an x and seeing if you can just take the limit of the new function of x. Okay, as n goes to infinity, or as x goes to infinity, I mean, the changing to x doesn't cause any problems. Okay, so what is this limit? Well, you can put this into your calculator or try and solve this. This is e squared, right? The limit as x goes to infinity of 1 plus 1 over x to the x power, that's the definition of e to the first. But you change the power of e based on whatever this is. Like so, the limit as x goes to infinity of 1 plus, this is the definition of e. This is e to the first, right? But you could change the power on the e based on whatever you make this. Okay, based on properties of logarithms, we can combine these two logarithms. Okay, now we could go ahead and rewrite this as just replace n with x, but we could think about using this theorem here. So we just look at this inside of the natural log. We just look at this sequence as its own sequence, 2n squared plus 1 over n squared plus 1. So let's do that. So if we had another sequence, so let's call this b sub n. Okay, what is the limit of this sequence? Well, if we replace n with x, is there any issue? No. So what is the limit as x goes to infinity of this? We divide the numerator and denominator by x squared. So we've got 2 as x goes to infinity, this goes to 1. As x goes to infinity, this goes to 2. So, okay. Now, so we have the limit of, we've got the limit of this sequence here is equal to 2. Is the natural log continuous at 2? Yes. So that means that the limit of a sub n is just equal to that function, which is the natural log evaluated at 2. And that's the limit of this sequence. Now, we could have just replaced n with x and taken the limit as x goes to infinity of the natural log of this as a function of x, but there's different ways of looking at it. You know, even if you have the limit as x approaches whatever of the natural log of some function of x, you can, with limit properties, you can say this is the natural log of the limit as x approaches infinity of f of x. Limits are nice that way. Limits are really easy to kind of just, they're really flexible in this way. Okay, so let's try and use this theorem. So let's take this as its own. We'll call this C of n. Okay, the limit of C sub n is equal to obviously infinity. As n goes to infinity, n goes to infinity. Okay, is the natural log function f continuous at infinity? So what that means is that any, like if it's any positive number is the way I would look at that. Yeah, we know it is. Any positive number that you can evaluate natural log at, and infinity is, no matter what, is always a positive number. So according to this theorem, I mean, they're saying it has to exist, but I'm using it as an engineer. According to this theorem, as a mathematicians would get mad at what I'm saying here, because this theorem is just saying that it has to exist and equal to L. Infinity is not a number, right? But what this theorem is saying to me is that we can say that then if B sub n is equal to the natural log of n, then the limit of the sequence B sub n is just the natural log of infinity, right? The function is the natural log of what was, in this case, L, which was infinity. What's the natural log of infinity? That's infinity. Okay? So now, is arctangent continuous at infinity? Yeah, arctangent is, the domain is all real numbers for arctangent. So the limit of A sub n, which is what we're looking for, is arctangent of infinity, which means the limit as like x approaches infinity of arctangent of x. You can think of it that way. So I forget what that is. It should be an actual number. Pi over 2. Okay, looking at this, when I see problems like this, I kind of think, can we replace this with like some sort of trigonometric function, right? Because like trig functions, like sine and cosine, oscillate between 0 and 1. So maybe we could look at this from the perspective of a trig function. But, okay, 0, 1, 0, 0, 1, 0, 0, 0, 1. So to me, what that's suggesting is that it's, so 0, 1, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 0, 1, like that. You just keep, you do an additional 0 in between the ones. So as that goes to infinity, what's going to happen? You'll have you can think about it like 1, infinite number of zeros, and then 1 again. Okay, so what's that approaching? That's still, no matter what, it's always going to be oscillating between 0 and 1. I don't know if you call that oscillating, but it's like you don't know, it's going to be, you don't know whether or not you're going to get 0 or 1. So there's no limit. It's divergent. And I guess you'd call that oscillating. It's like a certain specific type of oscillation. It's not going from like 0, 1, 0, 1, but it's like it's oscillating in this way. This just keeps getting longer. So divergent.